Hello folks, Rashid here. Thank you so much for joining. I'm starting a new series and it is MicroArchitecture. In this video, I will give you overview of what I plan to cover in this series or playlist. So this is what we're doing right now, and this is what we did, and this is what we're gonna do. So a better place for this one is if I could show you. You can go to this website. It's there on my YouTube channel about page as well. So click there and it will take you to this page. Okay, this is part of what I call the foundations, the fundamentals of digital IC design, and it's track 1. So in this track, if you see these green ones which are already done, I need to update website. So digital design basics, combinational logic is done. Digital design basics, sequential logic explained. Then in that series, the next one is this RISC-V architecture. This is what we just finished. All right. So this is what I'm saying. These two are done, right? And now we are into this one. After I finish this RTL part, then will come this and then the physical design. Okay, so I will cover some additional stuff, especially in physical design, because I'm going to use open source tools, and the OSAC 1.0 that I developed over here. I'm going to take it all the way through RTL verification and physical design. But anyway, this is what we are doing right now. All right, I think this is going to be a stretch that if I finish in November, I think it might take longer, but we'll see. But a lot of interesting stuff is coming. Where do I go? Yeah. So what this is, so what is microarchitecture? What exactly I'm going to cover in that one? So microarchitecture, the prerequisites are this one. So if you haven't done these ones, strongly recommend you. I think you might not. I'm not going to explain the basics here and this here. I'm going to assume that you have gone through the architecture series, and as well as you understand the basic digital design concepts. So if you haven't done those, please follow those playlists first and then come to this one. And also the other thing is, in the microarchitecture, even though during the architecture I covered CPU or core as well as non-core part, we built a small SoC, right? But in this microarchitecture, my plan is to cover first core part, first CPU, and even within CPU, if you remember, we covered CSR and that stuff, exception, interrupts, and all that. For the moment, I'm gonna hold that. I will only in this playlist will cover these 37 instructions that we gone through. These arithmetic, logic, shift, comparison, and control, memory and control. So the one R type, I type, SB type, those are the jump and upper ones, those ones. Okay, so this is core part. And I think you will have a plenty to learn from this one. What we'll do is after that, we go into system Verilog and implement all this. And then later on, series will come where I will cover the non-core part and then we will combine the SoC. Okay, so we will look into different, all these instructions and create a microarchitecture, or what microarchitecture is, a block diagram. So we will have a block diagram like this. So we will start with some of the core components, like you can see here, program counter. We will, for now, assume we have a separate memory for instruction and data. Where's data memory? Okay, gone from here. Okay, there's supposed to be a data memory here too. But anyway, the point here right now, I want to show you this different block, then ALU, and then register file. Sign extension, adder for, and multiplexer. So whenever the more components come, we will add them. And basically what we will learn, we will go one instruction at a time. So the very first instruction we will look into add I add immediate, because that is used to assign a value to registers, right? So kind of that is really the basic one, the first one you want to implement, because you want to initialize your register with something. Because in RISC-V, all the operations happen on registers, not directly on the data in the memory. So you need to bring memory data from the memory into register. But first you can assign. That's why we use add I and then load and then store, and then we will go through R type, all immediate type, all SB type, and then other instructions. Okay, so goal here is to create proper connectivity between these different basic building blocks, right? And gradually, first, for example, this instruction 32-bit comes. We know that 19 to 15 will go here. This is for I type. Bit 11 to bit 7 will go to this one. And then once these two, some data will come, and I'll explain those from the next time. The intention here is not to explain you everything. Once to get a data here, and then address here, and the data comes at the output, we will decide what is connected to ALU. Output of ALU we need to probably connect back. We need to do sign extension. I didn't draw these connections here. And this one, and if we want to write on a data memory, then we also need to make connection there. Okay, so we will start on that properly next time, but basically this diagram with all the instruction later on, for example, right now you are connecting ALU. For example, right now you have, here I can't see it. All right. Right now you connect to this one, but in future if some other data is coming from here, so you can tie this one, and then through the control you can decide this one or this one. Then this is also through the control you decide within ALU you want to add things, add these two, subtract these two, compare these two, and these two, or these two, blah blah blah, whatever within arithmetic logic unit you want to do. Correct? Similarly, you might want to connect different bits from this instruction side here, and the data can come from data memory that you want to write into a register file, or output of ALU that want to register file. You would put a mux here too. So those are things you will learn. Once you do first few instructions, we implement those. Rest of the instructions shouldn't be a big problem. And also it is much easier because we're not going to add additional pipelines. It's just a single cycle, and your cycle starts here. So your sequential elements, these yellow are, they move data from input to output, or in the case of register file, you write into a register, which is the same thing. Basically, register file is like a register. So the value goes from input to output. So reading is just reading the output. It's always available, right? But writing into it is always on the rise edge of or fall edge of the clock. Okay, so once you put something in program counter, that means address of the instruction memory, data will be here, data will be here. We will eventually, data will be available for us to put right back into the register file when the operations happen, right? And then you have separate instruction where we take from register file and read in, write into the memory. But basically your time starts at program counter and ends on register file writing, for example. So that is one cycle. So this processor that we are developing is a single cycle processor. So it doesn't have all those complications, adding pipelines, hazard, and this and that. But in future versions, when the second time I come, maybe we can add some of those things to give you that experience. But first, here, goal is that you understand how to create microarchitecture, and after that, how you create a hardware and system Verilog. Okay, so once you create this, and you will see that we will have all these multiplexers so many places, because on multiple instruction we're probably using multiple ports of these. Typical analogy that I tell people is that, okay, think of this, that your basic places where you kind of go and stay for a while are your home, school, your company, wherever you go for recreation, or other places, right? So at certain time you leave, let's say multiple people come here, we put there's a traffic control light here. They decide if multiple people want to go here, okay, who needs to go first, who needs to go second, right? So these road structures are kind of your data path. There is already a connection there. Which one needs to go at which time we control through the control circuit. So our microarchitecture is made of a data path. So we draw all that data path here. So like we draw all these block down. This is not right now connected, but eventually things will be connected based on which instruction it is. So you connect all of them, and through multiplexers control or ALG control, right? These are your what or depending upon instruction we define these things. So this is your control, and rest of the connections already wired. Those are your that is your data path, and these things are your program counter, your memory elements, your register files, or in case you want to write into the memory, that is also. So writes are always on the clock, reads are not on the clock. It's like combinational, right? So you understand the analogy of it? So one other thing that we are going to do here, and that is interesting, I feel that is something I don't see in a lot of these academia series, that the microarchitecture that we are going to build here is not just a paper diagram like this. It will be very cluttered. Ideally, what you do is you create this one, and from this one you start creating hardware or you start coding it, right? But what I'm going to do here is we are going to create models of all of these in Python. Okay, so this part we will create. We will have entire microarchitecture, even kind of this based on clock kind of reading or writing, kind of model that properly in Python. So entire hardware, this is called system level modeling. People use C, system C, or other things because before you even go and system Verilog, and there are a lot of other things you have to deal with. And this will be kind of modeling of the hardware will be quick, and we can test it. You put one instruction, you can check, okay, you can write equivalent of this in Python, and it's still kind of sequentially executed. I mean, even in simulator it's sequentially executed, but eventually we'll build the intention of the hardware. Okay, so that will be, you will see that will be something different in my series. And goal really is that once you have this built, building this will be very easy. This will also be a kind of a documentation. I might use AI a lot, but once I have this, hey, convert this into system Verilog, but then I will in detail review that code, because the better code you have, the easier the physical design gets. And since I have a lot of physical design experience, I will be building the system Verilog code in a very efficient way, so that we have very optimized, synthesized and placed and routed netlists. Okay, but another second or third probably benefit is that once we have this one, once we have a system Verilog code, the stimulus that I will be writing to give this one and monitor outputs, once this is verified, this will act as a golden one. We will run those through the simulator, give it our input files and output files are generated. We read those. So entire automation that we eventually create here, we will compare these two. Okay, and we'll say, okay, if this code is working fine or not. So it will also serve that purpose. I will show you every time, the very first time, it might take a little bit of time for us to kind of code all those things, and I will show you individual code in Python. I'll give you files, you can use them, you can simulate them. All right, so I think it's a lot of fun. This first time training like this I'm giving, so I'm super excited about it, and I'm sure we will have a lot of learning on it. All right, that's it for now. And by the way, this will be for the members only, although I will keep giving free videos. All right, that's it for now, and yeah, we'll see you pretty soon with our first lesson on add I instruction, and we'll build microarchitecture and Python code for that. All right, see you, bye.